So I'll walk you through the sheet while they're being passed forward. I thought we'd do a little bit of show and tell. Okay, so this class is about these little boxes. I'm really excited about these boxes. I designed them myself. Okay, I built the first few, and then I had help kind of replicating them. Can you guess what's in the box? No, it's much it's much lower tech than that. Just blur things out. Yeah, it's a filter. It's a passive RLC filter. It has two audio, like, you know, 1/8" audio jacks, like the headphone jack on your phone. So it's just a passive RLC filter. It's got one inductor, two capacitors in it. You can drive it from either side. The impulse response is slightly different depending whether you drive it that way or that way. And this is our channel, okay? And the goal of the class is to build a communication system that moves bits over this channel, okay? So the way it works is you take, say, a laptop and take the, or your phone for that matter, okay, and take the headphone jack on it and use that to drive the input to this, okay? Then take the output of this and feed that into either the line in or the mic input on another laptop, okay? And then your job is to move bits as fast as you can through this filter, okay? So more precisely, the goal is to create two MATLAB functions, two M files, one for the encoder side, one for the decoder side. The encoder side will take a bit string you're trying to send, so a vector of bits, map it to a wave file. Wave is just uncompressed audio, okay? So that's the transceiver that you designed, the encoder you designed, just a MATLAB script that just maps bits to audio files. You play the audio file through this thing as though it was a song, okay? Just out the headphone jack on the PC. You make a recording of what the receiver hears on the other side of the filter when you're playing that, okay? And then the decoder that you design takes that wave file that comes out of this, okay, and then extracts the bits. That's the goal, okay? This whole class is built around that goal, okay? Learning how to do that and how to do that well, okay? So you're all electrical engineering, upperclassmen, MEng, PhD students, whatever, okay? So I'm sure you can all move some bits through this. If I gave you this filter and said, okay, go to it, I'm sure you can devise some way of moving some bits through this at a reasonably low rate, but the goal here is to really push the data rate, okay? And, you know, in prior years, depending on what power level we allow, what sampling rate and so on, people get, you know, on the order of like 50, 100 kilobits per second through this little filter, which is quite amazing given the bandwidth of this thing. This is not a real wideband object, wideband filter we're talking about, okay? So that's the goal. The class is designed around both classes, 467 and, okay, sorry, 40. I still use the 3-digit numbering from when we used to use 3-digit numbering. So 4670 and 5670, the goal, I'll talk about the differences between the two classes shortly, but the high-level goal for both of them is to just learn how to move bits through this filter. And in particular, we'll learn how to move bits through this filter using a signaling scheme called OFDM. You might have heard of OFDM. It's kind of the best practice for communicating digital information, i.e. bits, over channels that are LTI with noise, okay? And this channel is the LTI plus noise, so OFDM works well for this. Many channels that you find in practice can be modeled as an LTI filter with noise, okay? DSL lines, cable modem, Wi-Fi, LTE, lots of stuff. Okay, so if you can understand OFDM on this box, okay, you can understand OFDM on lots of similar systems, including all the ones I mentioned. So you're kind of in a good shape to understand how Wi-Fi works, how LTE works, and so on and so forth. DSL, cable modem, okay? Everybody have the sheet? Okay, so that's the show and tell. Thank you. So let's kind of walk through the sheet here. So this is kind of a long, hard slog to go through this sheet, okay? And I think it's a good idea to walk through it and make sure we're all on the same page regarding expectations and policies and stuff. It's kind of slow, it's kind of dry, I know, but I think it is a good practice. There are seats up front here. Okay, or not. All right, so this is ECE4670 and ECE5670. So these are two classes on kind of the same topic that will meet jointly during this period. And there are certain differences in terms of the course requirements and so on, and the prerequisites and so on that, that I'll get to shortly. Anybody else need a sheet? This one? Okay, the course, the catalog description is given there. I'll say about 4 years ago, we completely redesigned this class. Prior to that, the prior to that, the class, well, it went through a few forms. Probably the most recent one took the form that this class exists in most schools around the world. That is a pure theory class that doesn't involve building anything and kind of skims over a lot of the kind of messy real-world stuff like synchronization that ends up being really important if you're trying to build a working system. It doesn't really have like a really clean theoretical story about it. Okay, maybe I should leave the extras. I'll put them there. So anyway, prior to that point, this class was kind of a pure theory class that just kind of emphasized the math. You didn't build anything. It kind of skimmed over a lot of the really nitty-gritty details that aren't really so clean for analysis purposes, but like are really important. Okay, and nothing against that version of the class, and it's the version that I took as an undergraduate. I was not an undergraduate here, but where I was an undergraduate, we had a similar class. And then for various reasons, 4 years ago, we decided to kind of throw that version out and start over. And we ended up with the current version of the class, which is a CDE. So it's a design class. I think it's a good class. I wish I could have taken this class as an undergraduate. The TA I had in the spring when I taught it told me he wished he could have taken this class as an undergraduate. I think it's a overall good class. I think one distinguishing feature of it is that it's kind of unique in that we do some non-trivial theory in here. We will prove theorems, okay, about how to communicate digital information over certain kinds of channels, okay, and then we're also going to build systems, okay, and debug them and get them working and compare how the designs, relate, compare to each other and so on, compare performance metrics and so on. So the class really involves this, a non-trivial amount of like roll up your sleeves, hands-on debugging, get it to work, and a certain amount of non-trivial theory. And the two really interact quite closely. In order to build a system that works really well, you have to understand the theory. And you don't really understand the theory until you try to build it and see, where the theory really is airtight and where it's kind of a coarse approximation. And I do not know of a course that uses so much theory and so much hands-on skills kind of in one class. Certainly there are theory classes. I've taught many theory classes over the years. There are really hands-on classes that touch on a bit of theory, but it's not really like a core part of the class. This class is designed to really kind of combine the two in a substantial way. So I think it's a bit unique that way. Okay, prerequisites. So all the formal prerequisites are listed here. So for the 4,000 level version, for 4670, it's ECE3100 and 3250. 3100 is offered in the summer and the spring. It's not offered now. If you've not had a class like that or kind of equivalent to that, this is not going to fly. I'll tell you right now, it's not going to fly. 3250, if you've had a intro signal systems class like 2200 but not 3250, you're taking 3250 now, you should be okay. But you need some probability. You need some probability exposure and some signals and systems exposure. Those are kind of necessary. For 5670, it's sort of similar, except that you're going to need some random process background. So if you're taking, I still call it 411 from the 3-digit numbering, 4110, if you're taking that now this fall with Qing Zhao, and you have a class like ECE3100 in your background, you should be fine. If you haven't taken a class like 4110, I think you should enroll in it this semester to take 5670 ideally. We can talk if you like, but that's one of the distinguishing features of 5670 versus 4670 is it will use some of the random process math that we'll kind of skim over in the 4,000 level version. Okay, so you got to kind of pick that up somewhere. 4110 is a great place to pick it up. Okay, because the class was redesigned about 4 years ago and is kind of unique, I don't really know of a good book that covers what we need to be covered. I started writing one over the last couple years. I used it in the spring when I taught this class. It seemed to work pretty well, so we'll go with that. So I will post chapters as we go that hew pretty closely to what I do in lecture in lieu of a required textbook. So going down the line, I'm Aaron Wagner. I'm the instructor of the class. Hello. This is what I finished 11 years teaching at Cornell in the spring, actually. It's amazing. The first few years are really long. After that, it goes really fast. So I'm an associate professor of electrical and computer engineering here at Cornell. And my research is in telecom, more on the data compression side than on the digicom side. But the two are actually very tightly related. And I work on both. We do have a teaching assistant, Umair Biljan. Why don't you stand up so people can see you? So Umair is a PhD student here in the department. We are really lucky to have a PhD student TA for this class. I was a bit worried given the pre-enrollment that they might say, oh, we need to allocate the PhD TAs to other larger classes, and I guess you can just, do it on your own. But they didn't do that, and so we have Umair, so we're very lucky. Okay, lectures, here we are. This is certainly not my favorite room. I wish the board was a lot bigger. I just use the chalkboard exclusively, but it will suffice. The plan is to video note every lecture. Probably this is not your first experience with video note. Although I guess we have some MN students here. It might be their first semester on campus, so maybe I should say a word about video note. So it's a videotaping service. They're going to tape all the lectures, record all the lectures, I guess. Tape is maybe an antiquated. Anyway, so they'll record all the lectures. They'll be posted on a website. I will link to it from our course website. Historically, they go through and take, you don't just have like, a 75-minute video for the lecture with just that raw video footage along with the audio. They actually go through and sort of label it. They have kind of an outline, and then all the different topics that I cover in the lecture are listed along with what time in the lecture they started. You can just click on one, it'll take you right there in the lecture. Do they still do that? Okay, all right, so the cameraman doesn't know. I would assume so. So it's there's value added. It's not just a pure, historically at least, that's the way they did it. It's not just a raw video. There is value added. I think it's a great service. They do a good job. Students in the past have really liked it when we did this. The only one caveat I'll make is that this is not intended to be like an online course. So we need a critical mass of people here in the room. Okay, so if I end up lecturing to the cameraman and the camera, okay, then we might need to kind of change things a bit, okay? Because it's not an online course, so we need to all convene. And I understand people need to miss class occasionally for this, that. That's fine, that's totally understandable. But we need a critical mass of people here to look at each other and discuss and so on. I think that's kind of important. All right, discussion, that's Friday, 10:10 to 11 upstairs. So nominally, we have, it's in the schedule for every week. In a typical week, what will happen is Umair will solve problems in a workshop format. So we'll put a problem up, let people work on it, move around the room, give advice, answer questions, solve the whole thing, then in as much detail as needed, and then move on to the next problem and so on. That's a typical case. There'll be many atypical cases though, many exceptions to that rule. They will start this week, and this Friday I will just do a run through of how to how to use the filters for your labs. There'll just be a how-to on how to use the filters. That's this Friday. In future weeks we'll have prelim review. We'll do standards voting. I'll explain what that means in a bit. There'll probably be a couple of sessions where I will do a dedicated 567 lecture during that slot. That's just for the 567 students, etc. Okay, so there are a number of exceptions, but that's the typical format. I think in the course catalog, the discussion is listed as optional for 467 and required for 567. That's why, okay? So if you're in 467, then technically you don't need to attend any of the discussions. They're all kind of just bonus optional stuff. If you're in 567, there will be a couple times where I'm going to be kind of lecturing during that period. So officially it's required, but if you know someone, and we're not videotaping those, I don't think. So just these main lectures. So be aware of that. Anyway, so that starts this week. So it starts this Friday. Office hours listed here. We can move these if needed. I think it makes sense to wait until people's schedules settle down before we start optimizing that. So here's initially the schedule. Okay. So now we get into the contract part of this. So like I said, it's kind of a long slog through this really dry document. So just kind of bear with me here. So much of the rest of this is I view it as a contract, okay? It's like a social contract for this class, okay? And it provides you with certain rights and responsibilities and me with certain rights and responsibilities. And over the years, I've kind of honed these rules so that they simultaneously meet your needs and my needs, okay? So first of all, let me just say, you all have needs, and I recognize that, okay? So you're Cornell undergraduates, MN students, you're taking 5 classes, 6 classes, 4 classes. If you're an MN student, you have an MN project. If you're an undergraduate, maybe you're on a student project team. I don't know, the concrete helicopter or whatever, right? You're working in the maker lab, okay? You're an officer in your fraternity, you're an officer in your sorority, you have a boyfriend, you have a girlfriend, your mom expects you to call. Okay, you have a lot of demands on your time, okay? And I understand that. I was an undergraduate once myself. I interact with a lot of undergraduates. Okay, so I understand that, and I understand that as a result, you need a class that, while challenging, okay, does not like gobble up huge, like uncontrolled amounts of your time, okay? And also a class that's sort of predictable, so you kind of know when it's going to be busy, you know when it'll be less busy, so you can focus on other things, you know when you can turn in things late, when you can't, what's allowed that way, what's not, and so on. So you need kind of clarity so you can plan, and also like a certain amount of containment. Okay, those are your needs. Okay, let's talk about my needs. So teaching this class is, I would say, probably less than a third of my total responsibility at Cornell for this semester. Okay, so just as you need a class that doesn't like expand like a gas to kind of, you know, consume your entire schedule, I also need a class that does not expand like a gas to consume my entire schedule. Okay, and the way classes on my end, the way classes tend to expand to consume my entire schedule is one of two ways. One is email. I just get buried in email. Okay, so there's kind of a lot of you and there's not so many of me. So like if all of you just kind of like send an email to wag at cornell.edu, whenever any question pops into your head related to this class, I can get buried in email. That's one way it can happen. The other way is if I'm negotiating like deviations on due dates and stuff individually for everyone. Okay, so homework, you know, 2 is due Friday, and you're going to turn it in on Monday, and you're going to turn it in like late Friday, and what happened to your homework 1? I kind of forgotten, or maybe I'm confusing you with you and stuff, and like, you know, I can go crazy with that stuff. Okay, so I need a class that, you know, does not like completely fill my inbox with a lot of stuff that I have to try to like, you know, crank through. Okay, and also I need the logistics to kind of run on autopilot to some extent. So I'm not negotiating every homework with every student, okay? All right, so all these policies have kind of been honed with these two competing needs in mind. Your needs, my needs, okay? So let's start with the first thing, Piazza, okay? So this is in the kind of email department, like preventing my email from just getting out of control. Okay, so we set up a Piazza site. Probably many people have used Piazza. If you have not, it's basically just like an online chat board, I guess. I'm not sure how you describe it. Just an online chat board, I guess. But it's well run. Anyone can post, any student can post a question. I guess technically I can post a question too. I never really thought about it. Anyone can post a question. Anyone can answer the question. Okay, so if someone posts a question and you think you know the answer, you can post the answer to it. And then Umair and I can sort of certify that an answer that's already been given is a good one, it's correct, or we can correct it, we can supply our own answer. And this is great for allowing you to get help quickly, get answers to your questions quickly, and also like not having me getting buried in email. Okay, because if one person answers a question and it's posted on Piazza, then like, you know, everyone can see it. And also Umair can help me answer stuff, whereas if you just email me directly, then he doesn't get it. Okay. Also, students can answer each other's questions, so it kind of scales well. Anyway, I've had a good experience with that in the past, so we'll do that. Our emails are here. You know, if you have something that's kind of a personal nature, not all appropriate for Piazza, by all means. I don't want to say don't email me. Okay? Don't take that message away from this. Okay, you can email me. Okay, just generic questions related to, you know, how to do homework problems and logistics and just subject matter of the class that might be of interest to other students. Please post that on Piazza, and then restrict email to just stuff where like it needs to be a one-on-one thing. Okay, Blackboard. Not much to say about that. That's the website we'll use. It's basically a repository of everything. I'll put this up there. It's not up yet, but the PDF of this document, you know, all the homeworks, the labs, and we store our grades in there and everything. So it's kind of the go-to place for the class. The one thing that's there that I'll call your attention to, it's up now, so you can go look at it now, and you might not know where to look for it, is there's a very detailed lecture schedule. Okay, so from today all the way until our last lecture, which I think is November 30th or something like that. Yeah, I guess it must be November 30th. Okay, for each lecture between now and then, okay, there's a list of what I plan to cover, like exactly what topics I plan to cover, and I'll put links to the book chapters on that. So if you have to miss a class, you know, you can see ahead of time what I plan to cover. I do update that as we go to reflect what I actually covered as opposed to what I plan to cover, which is usually close to the same thing, but sometimes I'm overambitious in terms of what I can cover, so I fix that as we go. Okay. So the grading breakout, there's two grading breakouts. There's one for 4670 and one for 5670. So we'll have about 8 homework sets, so about 3% each. That's for both classes. That's for 3% each for 467, I guess 2% each for 567. We have 5 labs, and you see they kind of like grow geometrically in importance. So more on the labs in a bit. One prelim. This is the date I've been assigned, Thursday, October 19th, 7:30 to 9:30 p.m., 203 Phillips Hall. I do not pick the date. Okay, I just tell the department we need to have a prelim around this time, and they come back to me and say this is your assigned date. Okay, so that's why that's there. Please mark your calendars now. You get 2% just for the course evaluation. I'll say 2 years ago I taught this class and we had a grading breakout similar to this, and there were some complaints from the students that there was too much riding on the prelim. Like you can have like, a bad day the day of the prelim and it influences your grade a little bit too much. So your grade is too sensitive a function of this one test. So, me being as committed as I am to continuous quality improvement, I said, okay, well then the next subsequent year, so spring of 2017, we'll have 2 prelims, right? And then they balance each other out. And I think the prelims might have balanced each other out, but it was just too much work. We just had too much going. It was too busy for everyone. So, and we ended up having to like put off things and cancel homeworks and delay the labs and everything. It threw the whole schedule off. It was just too much. So I'm going back to 1 prelim. So we'll just have 1 prelim. And yes, there's a lot riding on it, relatively speaking, I guess. So, I don't know, it's kind of stuck between a rock and a hard place here. So we'll do 1. The 5670 grading is similar. So there is a final exam for that class and not for the undergrad version. And that's the breakout. The prelim is the same time. I haven't decided to what extent they'll be the same exam. They might be literally the same exam. There might be the 5670 prelim will have one extra problem or a different problem or something. They'll be similar though. All right, let's go to the labs. So the labs are really the core of the class, as I alluded to with the filter. So there are 5 of them. Labs 1, 2, 3, 4, 5. So let me just give you a quick rundown of how these labs work. So the first 2 labs do not involve any design at all. It's just analysis, okay? Like plot measure the impulse response of the filter, okay? Measure the frequency response of the filter, measure the noise floor, estimate how much synchronization skew, you have between the transmitter and the receiver, okay? So it's not designing anything, it's just like characterizing what we've got, okay? So labs 1 and 2 are both that. Those are both worth about as much as a homework. All right, then it starts ramping up. So lab 3 is the first design lab, okay? And so the goal there is to build a communication system, but the channel is not the filter for that one. Okay, so we're not using this for lab 3. For lab 3, the channel is just a MATLAB function. It's just an M file. It takes your transmitted signal, it convolves it, so like passes through an LTI system, it adds noise, and then hands it to the receiver. Okay, so that's sort of like an easier design problem because like there's no synchronization to worry about. There's no uncertainty about what the channel is doing. Okay, there's no question what is the impulse response. Okay, there's no question what is the standard deviation of the noise. Okay, that's all just hard-coded in the MATLAB file that's there for you to read. Okay, so it sort of simplifies the design problem in certain respects to kind of help you get your feet wet. Lab 4 is the first one where you're building, a communication system over the channel. For lab 4, the goal is not to like push the envelope performance-wise to get something working. And for lab 4, in lieu of a regular lab report, the way it works is everyone writes a proposed standard for how you would communicate over this filter. Okay, so standards are a really important part of communication engineering. Okay, so there's standards for all kinds of different systems. There's a standard for Wi-Fi. That's why an Apple phone can talk to a Cisco router. Okay, because there's a standard and both companies follow the standard, so they interoperate. Okay, writing standards, reading standards. It's an important part of the business, and it's a bit of a subtle art. Okay, and so I wanted to integrate that art into this class as best I can. So what we do is for lab 4, each team submits, instead of a regular lab report, just a standard for how their system works. Okay, and then Umair and I test all these designs. Among the ones that work really solidly, we pick the 2, say, standards that we like best, that we think are clearest. And then I invite those 2 teams to present their standard to the class. We'll do that during the recitation. The class votes to adopt one standard or the other. Okay, and then for lab 5, the last one, there are 2 parts. Part 1, everyone builds a standard compliant system. Okay, and if everyone achieves standard compliance, then your encoder should work with your decoder and vice versa, right? That's the whole point of standard compliance. All right, so that's part 1 of lab 5. And then for part 2, it splits between 467 and, I'm just going to use the 3-digit number. Is that okay? It's a lot. The extra 0 is just unnecessary verbiage, I feel like. Okay, so for the 467 version, part 1 is the standard compliant thing. Part 2, just like use this, communicate over this channel, and just get like the highest data rate you can. Okay, so just push the performance envelope. For 567, part 1 is standard compliant system over this channel. The other part is actually to build a working system over a wireless channel. Okay, so 567 will not use this filter for every lab. We'll use it for, for the second part of lab 5, we'll replace this with an actual wireless system. Okay. Okay. So that's the labs. So there'll be among the 467 students will be a prize for the highest performance for the second part of lab 5. I'll say I don't think these labs are like a great deal of work. I kind of designed them to sort of maximize the learning to effort ratio, as I call it. Does that make sense? Do you know what I mean when I'm talking about when I say learning to effort ratio? I know what I mean. Because, okay, can I relate an anecdote? So when I was an undergraduate, I wasn't an undergraduate here, we had to take one senior design class, like a capstone design class. Sound familiar? Okay, even though I was more on the math side, I was interested in the math side of electrical engineering, I ended up taking this VLSI design class because I got these really rave reviews. Everyone's like, you gotta take the VLSI design class, it's amazing. Okay, it will change your life, okay? It did change my life, okay? So we laid out the data path of a microprocessor in VLSI by hand. The data path was done completely by hand, okay? It took forever. All right, we had a team of 4 people. Each of us would work like, at least 40 hours a week. Okay, so multiply that out. Okay, and we barely get the labs done in time. Okay, and yes, a lot of people thought this was a really formative experience. You learn a lot. Your confidence really increases a lot. I saw it as deeply inefficient, actually, because I feel like everything I learned about the first 2 weeks of that class. After that, it was just pure overhead. Okay, it was just like mindless work in which I learned very, very little. Okay, so I resolved at that point, if I was ever in a position where I was going to teach a class like this, I would try to design it in a way that maximizes the learning to effort ratio. Okay, I did not think that was a good use of student time, the way that class was taught. Okay, so yeah, all this is being recorded. Anyway, that's the fact of the matter. That's the way I feel. So I'll tell you, I looked up like last year's designs. So for the part 2 of lab 5 for 467, okay, so the high performance system over this lab, okay, there was, I didn't look up the award winners, but I looked up the second highest performing team. Okay, their total design, encoder and decoder together, was less than 400 lines of MATLAB code. Okay, that's including the comments and all the white space that they used to pretty print it. If you delete all that, it's probably gonna be like 200 lines of code. Okay, if that sounds like a lot to you, go bring up a script you wrote recently. Okay, MATLAB lines of code go quickly. Okay, it's not really that much code we're talking about here. You gotta know what you're doing. Okay, so here's where the theory and practice intertwining come in. Okay, if you don't know what you're doing, it's gonna take a long time to do. If come lab 5, you've been following what we do in class and you're more or less on top of the class, okay, this is not something that's going to take you weeks and weeks to do. Okay, it does not take long to write that much code and optimize it. Okay, and speaking of learning to effort ratio, let me talk about CommCloud. Okay, so I'll give you a quick history here. Version 1.0 of this class, we had one of these for every student, and I just handed them out along with the cables. And I said, great, the lab is in your backpack. And you can use your phone, you can use your laptop, you can use anything that can drive these things, you can use that as your transmitter and receiver. What could be more convenient, right? Bad idea. Okay, because there's way too much variability from sound card to sound card among PCs. And so what would happen is, it'd work for the student on their laptop, and they'd send me their M files, and I'd run it, and it would fail catastrophically. And I'd say, it doesn't work. They'd say, well, it works for me. It doesn't work for me, right? So now what, right? Okay, version 2.0, we said do initial development wherever you want. Everyone gets a filter. We'll do final testing in the Linux lab, 213 Phillips Hall. That was better. Okay, that still caused problems. Too much variability, sound card to sound card among the PCs there. Moreover, you had to get 2 PCs next to each other that were open so you could run the cables between them. The cables are only 3 feet long, okay? And certain times of the semester, the place is filled with VLSI students, right, with their rectangles, and you can't find, one open computer, much less two that are next to each other. Okay, so logistical problems. So enter ComCloud. Okay, so we just did a cloud-based solution. Okay, we have a server. It has a bunch of external USB audio hardware on it. We attach a couple of these to it, and we have Python code. Now you take the WAV file that you want to send through the filter, and you just type cc play for ComCloud play. Cc play, name your WAV file. It sends the WAV file to the server. It queues it up behind any transmissions that have been received earlier that aren't done yet. Okay. When it's your turn, it plays it through the filter. It makes a recording of what the receiver hears when it's playing your signal. Okay. Sends you the WAV file back of what the receiver heard, ends up in your current working directory, and then you run your decoder on it. Okay. It is very repeatable. The server is locked in a server room. No one touches it. The audio settings don't change. Nothing changes with it. So it's very repeatable. If it works for you, it will work for me. Moreover, you can work on your lab anywhere. Okay? Any place you have an internet connection, you can be on the beach if there's Wi-Fi there. You can be at your parents' house, your apartment. You can be in Duffield, wherever. Any place you have an internet connection, you can send a file to the ComCloud server and have it play it through and get a result back. So you can kind of debug your server or your design anywhere. Yeah?
How long of a process is that to get the information back from the server?
It's minimal,
okay.
I think. Yeah, it's a few seconds.
Oh, awesome.
I think, yeah. I mean, it depends how big of a WAV file you're trying to send it, but actually it will flag. So this is also, speaking of honing things, we've kind of evolved this code. So the first version of this was actually written by Noah Levy, if anybody knows him. So you guys know him? Okay, great. So one of the earlier students in this class, he wrote version kind of 1.0 of that code, and we've kind of honed it over the years. It's now maintained actually by the CAC people upstairs in Rhodes. Okay, so it's all professionally done now. But it runs some tests on your WAV file before it actually sends it, and one of the tests it does make sure it's not obscenely long. Because we had an incident where someone through a typo, added a couple of extra zeros when they created their WAV file. So the WAV file that was like 10 minutes long or something, they tried to send to the server, and it just choked it and broke it. And this is like right before the lab's due and stuff. So now the client will kind of test your WAV file before it sends it. So yeah, it's pretty fast, back and forth. I think, I'm sorry to say, it loses some of the magic. Okay, in the original version of this, it was kind of cool because there'd be data on this laptop, and you'd run it, and suddenly it would appear on this laptop. Okay, and I must say, there's something kind of magical about that. There's something kind of inspiring about that, and that's all lost now. It's all just kind of in the cloud. You just send this WAV file and get a WAV file back, and you have to trust me that there actually is a filter over there. It's not just like some M file, okay, that just pretends to, emulate. If we have actual hardware, actual filters and stuff, it's all still there. I'll show you a picture of it as we go on, if you don't believe me. And we're adding wireless to it. Right now, it's all audio band. It just has 2 of these filters on it. But for 567, we need the wireless. So by the end of the semester, when Lab 5 arrives, hoping to have we have the radios, we just need to kind of hook them up and so on. Okay, we're getting near the end. I know this is a long, kind of boring slog through here. So let's talk about homework. So I said this class, we do theory and we do implementation stuff. The homework is more to learn the theory and to emphasize the theoretical concepts. We have about 8 homework sets. With regard to collaboration stuff on homework, let me be very clear about this. How you do the homework, I don't care. I really don't care how you do the homework, okay? If you want to work on your own, compare answers with a friend, great. Work with a friend and do it, great. Talk to your friend who's a PhD student at the university, great. Talk to Noah Levy, fabulous, okay? Doesn't matter. Okay, Wikipedia, fine. I really don't care, all right? You're upperclassmen, you're master's students. I trust you to do the homework in a way that kind of maximizes your own learning. I'm not going to force fit my own view of how this should be onto you, okay? A couple of ground rules and a warning, however. Ground rule number 1, in your own words, please. Okay, so verbatim copying of something that someone else wrote is never an acceptable thing to do. To attach your name to someone else's prose, okay, it needs to be in your own words. In your own handwriting, that's the second ground rule, okay? Because text, as kind as it is to type up your homework, it's a little bit too easy then to kind of cut and paste, between people and year to year and so on. So in your own handwriting. I have had, I'll just say as a caveat, I have had people who have, because of some mental impairment or physical impairment, they not really able to like handwrite stuff, so they prefer to type it. If that's you, we can work it out, no problem. But for anyone who's not in that situation, handwritten stuff. So those are the two ground rules. The warning, I'll say, the prelim. The prelim is going to be testing more the theory side, naturally. The labs are for doing the hands-on side. For the prelims, that's the usual thing. Everyone works individually, and there's no network connectivity available. Okay, so if you get in the habit of solving the homework problems by just not really even trying them on your own, and just getting help from someone or looking up on Wikipedia, then come the prelim time. Okay, you might not really be well versed in how to kind of get yourself unstuck from a problem where you're not really sure how to proceed. Okay, so I would keep that in mind. One other comment about homework, perhaps because okay, I'll just say my general feeling on homework, when I assign X as a homework problem, I do not view that as a test of your ability to do X. It is really a declaration on my part, it's an announcement on my part, that I'd like you to know X. And however you want to find out X, however you want to learn X, is up to you, okay? But it's not a test. That's partly why I don't really care how you do it. Since it's really an announcement that I want you to learn X and not a test, I'm happy to show you X, okay? If you come to my office and say, I don't know how to do X, I'm just going to show you how to do X, okay? I must say, speaking of, okay, this has become kind of an event session about my undergraduate education, but I'll say, when I was an undergraduate, few things bothered me more than when I go to office hours, and the instructor would, rather than just kind of answering my question directly, the instructor would sort of clumsily sort of draw it out of me. Like I say, I don't know how to start this problem. And they'd say, well, does it remind you from something in lecture? It's like, well, no. I mean, that's why was it remind you from something in the book? It's like, well, no, otherwise I would have gone with that. Well, how would you approach it? It's like, look, you're a professor, I'm a student. Teach me, right? That's why I'm here, So to me, and if you come to me and in an office hour and say, I don't know how to do problem 1, I'll say, okay, let's talk about how to do problem 1, and I will just show you right there how to do problem 1, okay? I think actually we're at our most receptive to new information. Here's me being the armchair psychologist now. We're our most receptive to new information when we're stuck on something. Okay, I see it in myself when I work on research problems. I see it in my PhD students when they're working on research problems. I see it in students in my class, okay? I don't know exactly what's going on. I think we all have a certain amount of ego. We think we know what we're doing. Everything's under control, and that ego kind of blocks certain new ideas. But when you're confronted with a problem you feel like you should be able to solve and you can't, suddenly you're just receptive to new information in a way that you're just not in your normal state. So if you come to me in office hours and you're in that state, I'm going to take the opportunity to cram as much information into your brain as I can, okay? And I do that by just showing you the answers. Okay, so yeah, I'll just show you how to do problems. Umair has marching orders to just solve the problems for you, so you can go to him as well. I'll say, I think people tend not to believe me with this. So early in the semester, I get very little traffic in office hours, and I don't know, people are just trying to do it on their own. By the end of the semester, my office hours are like one big homework party, okay? And we're working, which is the way I like to see it, honestly. So take advantage. I have colleagues, by the way, who are like aghast at this. They say, you mean you just show students how to do the problems? I say, yeah, I just show students how to do the problems. Isn't that what I'm paid to do? What do you do? Something I feel rather strongly about, actually. Okay, so in terms of this, the system, for kind of writing on logistics, writing on autopilot, the next two bullet points are, not bullet points, the last two paragraphs are about that. So due dates, so normally we'll hand out stuff like, Thursday and weekend, and then it'll be due like Friday, 5 p.m. week N+1. For the first part of the semester, I try to hand out like a lab and a homework together. The homework is due the subsequent week. The lab is due the week after that. It's not really that the lab takes 2 weeks to do. It's just that it's a little bit more constrained, and because you need access to the ComCloud server to do it. Honestly, this is maybe kind of a throwback to back in the days when we were actually wiring stuff together. So maybe it's not so important now. But anyway, bottom line is, first part of the semester, it'll be kind of homework lab. That'll be the rhythm of it. Later part of the semester, you got prelims, you have multi-week labs and stuff, so the schedule becomes more kind of ad hoc, but that's the way it'll work, at least initially. For late homeworks and labs, there's a paragraph on that. So bottom line is, you have 2 lates you can use. You can use them on any of the homeworks, any of the labs, except for 4 and 5, which are kind of special. And the grace period on a late is Monday at 5 instead of Friday at 5. So it gives you like an extra weekend to do it. So the prelim exam, that's in the evening, as I mentioned. There's language here about how we handle conflicts and so on. In compensation for the out-of-class prelim, we'll cancel 1 lecture. We'll just out and out cancel it. It's almost surely not going to be the day of the prelim. Okay, it'll be a day when I'm traveling to go to a research conference. So I'll announce that later. And there's the final for 5670. 4670 does not have a final. That's that. There's a blurb here on regrades. Exceptions. Okay, so all of these kind of rules here about lates and regrades and makeup prelims and stuff are all to kind of handle what I consider, typical scenarios. If you have an exceptional situation, then come talk to me. We can work something out. I will grant exceptions, but only like in exceptional circumstances. Okay, so like, hey, Professor Wagner, I have kind of a busy week this week. I have another prelim. Is it okay if I turn the homework in on Tuesday or whatever? Okay, my response is generally to that going to be, that's what the lates are for. You can just use a late. You don't have to tell me you're using a late. You don't have to tell me you're using a late. You just submit it late. The grader will mark it late when the Dropbox is emptied and so on. I do occasionally have students, they have a death in the family or something. If that's you, then come talk to me. Those are exceptional circumstances. We'll work out exceptions to all this. All right, almost done. This last bit on course materials, I didn't used to have anything like that at all, that paragraph. And then a few years ago, I found that I had been teaching like ECE3100 at the time, and like every write-up, every handout that I gave out for that entire semester was all on this like for-profit webpage, available for you to download if you just like sign up for their service. And it wasn't just me. I mean, they had a lot of classes like that. So I'll say as a college professor, I have kind of mixed feelings about that. On the one hand, like I want to disseminate knowledge. So if people download these things who weren't in my class and they find them useful, then great. That's, I'm happy to see that on some level. On the other hand, this is a for-profit company that's kind of making money off, all the work that we're doing here, and we're not really in the loop at all, which is, I think, kind of a problem. And copyright can actually get kind of messy there because we can get permission to, use copyrighted stuff for this class. That does not give us permission to post it online. So if students take it and then post it online, then the original copyright holders get mad at us, and messy. Okay, so bottom line is like all the materials, they're yours to keep. I hope you find them useful. Share them with your friends, share them with your coworkers. Just don't publish them or post them online in a way that's kind of equivalent to publishing them for the world to have. All right, academic integrity is here. Lastly, there are just a few books that I'll list as kind of useful references. I used to call this section Books on Reserve, and I would go to the library and have them put all these books on reserve. Do people even know what reserve means anymore? Okay, yeah, so this is time evolved. That's partly why I call it useful references to books on reserve. So it used to be, the library would have all these books, and if there's a book that was particularly useful, like a copy of the required textbook, they'd put it on reserve, and if a book was on reserve, you can only check it out for like 2 hours at a time. The thinking being that you don't want one student to check it out for like a month, okay, and that one student has access to it, and the other like n-1 students then can't get it. Okay, so they put it in just like so on reserve means you can only check it out for 2 hours at a time. I used to diligently put all these books on reserve, so that students wanted like extra reading or problem sources or whatever, they could go check the book out for 2 hours, work the problems, turn it back in, another student uses it. I used to do this as an undergraduate. I found it really helpful, and I got some stats from the library that like over the course of years, like one student had checked out one book that I put on. So evidently it's not really a thing anymore. To some extent these books are available online, so it's like you don't even need the physical thing anymore. Anyway, if there's an issue, if you would like the library to have a paper copy of the book and they don't, or if someone's checking it out and holding it and you'd like to use it for the class, and let me know. We can do that the old-fashioned way. But either way, these are good books to know about. So the first book, the Remoldi book, this is probably the closest, I have a copy of it here, this is probably the closest book to the class as I will teach it. It's not real thick, which is nice, so it's kind of a good self-contained introduction. Does not really cover OFDM or synchronization. It covers a lot of continuous time stuff. So it's kind of missing two important things for us and has kind of an extra thing that we don't need. But otherwise, it's pretty close. So if you want, like, you want to buy a textbook or rent a textbook or just, look at a textbook related to this class, this is probably your best bet for the 467 students. For the material for the 567 students, for the material that's only going to be in 567, like the extra lectures and extra homework problems and stuff, this is a good bet, and we'll slap it off. This is a more mathematical book. It's quite rigorous, and has all the continuous time stuff that we need. If you're sort of mathematically oriented and you don't like when like authors or instructors like tell you something and then pull the rug out from under you a time later because it was all kind of hand wavy, okay, then this is the book for you. Very rigorous. The third book is Rick Johnson's book, Rick Johnson et al. Rick Johnson teaches here in the department, of course. He's used this book for this class in prior years. It's kind of a unique book. It has a different take on the subject from most other books. It does not cover OFDM, doesn't really cover noise so much either. So again, like not a good fit for the way we're teaching the class now, but it's really useful, I think, in terms of just like getting receivers, transceivers to work in practice. It's really good at that. I don't have a copy of that. I couldn't find my copy of it. And then lastly, Seamus Waneth. This is a good book. It's wireless only, though. Okay, so the last part of the class, when you guys are working on Lab 5, or you all are working on Lab 5, I'll be talking about wireless communication. This will be useful for the 567 students. It's kind of FYI for everybody else. Whichever group you're in, if you want something to read, this is the book to do. Okay, that's it. Any questions? Like I said, I know it's kind of a long slog, but I think it's important to go through all that once so we're all on the same page. All right, no questions? All right, we have some time to talk about real stuff. So let me start with a course overview. I don't know if we'll do any real serious content today, but we can do some high-level stuff. Okay, so on some level this class is about like a problem and a solution to the problem. And the problem is digital communication and the solution is OFDM. Okay, so that's the mantra for the class. So let me talk about each of those in turn. Let me talk about the problem, okay, and then we'll talk about the solution we have in mind. Okay, so first here's the communication problem. It's not even the digital communication problem. I'll just call it the communication problem. Okay, so in the communication problem, you're an engineer, you're given a channel. Okay, this is like the physical medium over which we communicate. Okay, so it could be like a fiber optic cable, it could be a coax cable, it could be a twisted pair, it could be a slice of electromagnetic spectrum that you own, it could be two Dixie cups and a string. Okay, it's just some physical medium that you're trying to move information over. And usually, by the way, we think of moving information from one place to another at about the same time. You can also think about moving information from one time to another in the same place. That's basically storage. That'd be a hard drive, or like a solid state drive is basically doing that. It's basically moving information, in time, but in the same place. Okay, so we normally think about moving it from between two places. We can also think about moving it between two times. Okay, we'll focus on the two-place application, but they're really kind of the same problem, at least at the level of abstraction that we're working here. Anyway, you're given the channel. And you're given what I'll call a data source. So this is in some level the information we want to move. Okay, so it could be a text message, an email, a video, a speech recording of my voice, a drawing, whatever. This is the content we want to move. You're also given a data sink, which is like the ultimate consumer of the reproduction. Okay, so this is the person who wants to hear the audio recording, or wants to see the video, or wants to receive the email. Okay. Okay, so these are all given. The circles are given. You're given the channel, you're given the source, you're given the sink. Okay, your job is to design two things. one of which I'll call the encoder, and one of which I'll call the decoder. Okay, the encoder is going to take the data source and map it into something that can be input into the channel. Okay, and the decoder will take the output of the channel and map it into some form that's sort of consumable, digestible by the sink. Okay? So like that's your task as a communication engineer. Design this and design this. Okay? So I give you the fiber optic cable, I give you the video, I give you the end consumer, okay, who has like a certain, reproduction fidelity in mind. And I say, okay, map the video that you've got into some form that can be transmitted over the channel, and then take the output of the channel, which is generally going to be different from the input to the channel. Okay, and then map that in a form where you can render a video. Okay. This is a complicated problem. There's a lot going on here, right? It's not even clear to me a priori where to start with this. I mean, there's so much going on, right? There's only 5 blocks, so it seems simple on some level, right? But it's rather complicated. I mean, videos are very complicated. Fiber optic cables are very complicated. Human consumers of video are very complicated in terms of what they consider to be distorted and so on. Like, there's only 2 boxes of design, but these are principally very complicated machines. Okay, so how do we get off the ground with this? Okay, so for a long time, people just did kind of ad hoc stuff. They kind of pieced together, some electromagnetic theory, some circuit theory, some basic signal processing, some basic statistics, and kind of came up with ad hoc designs. In some cases, the source and the channel are kind of well matched, and so you don't have to do a whole lot. Like, if the goal is to send voice over like a twisted pair of cables to just someone who wants to listen to the voice, like this is like the classical telephone problem, right? Circa like 1940, okay? So what you can do there is just take the voice, put it through a microphone, you get an electrical signal, you just modulate the waveform on the twisted pair directly in proportion to the voice signal, okay? And then at the receive side, just take the electrical signal and just pump it through a speaker, and like that's at design, right? And for that particular case, that works pretty well. If you take voice though and you got electromagnetic spectrum, maybe it doesn't work as well, or fiber optic cable doesn't work as well, okay? Okay, so anyway, people had kind of devised like, simple reasonable solutions for special cases, and in general they had this kind of ad hoc way of doing it, okay? And then someone by the name of Claude Shannon came around in 1948 and introduced kind of a framework for doing these kinds of designs that nowadays we call the separation architecture. And he did not call it that, okay? In fact, this whole architecture wasn't even like mentioned explicitly in the papers that he wrote. He was a Bell Labs engineer. So this architecture I'm about to show you was not even described explicitly in his papers. It's implicit, okay? But afterwards, as people were reading through the papers, they found that you could kind of pull this idea out, and it ends up being really important. Okay, so what he proposed is the following. So what he proposed is a solution, like a way of designing this and a way of designing this. Okay, so the 3 circles are still given. So you're still given the same data source and the same data sink. Okay, and the same channel. Okay, then he proposed dividing this block into 2. Okay, and the first block we would now call a data compressor. That's not really the terms they used back then, but we would now call this a data compressor. Okay. The next block we would call a channel encoder. Okay, those 2 blocks comprise the encoder. Okay, at the receive side, the decoder gets split into 2 parts. This is what we call the channel decoder. Okay, and then after that, there's what back in the day they called the source decoder. We call it a data compressor nowadays. So data decompressor, I'm sorry. Compressor. Like that. Okay. All right. So Shannon had something in mind for these boxes. Obviously, just dividing one box into 2 in a And a diagram like this isn't really saying much. Okay, so where each of these boxes has a very specific function. So the data compressor maps the source to a minimum rate bit stream. Okay, so it's maybe easiest to think about the case where the source is not like an image or an email or some kind of fixed length entity that you're kind of like trying to download offline. It's better. He was a Bell Labs engineer. He was thinking about telephony. So think about telephony. Okay, think about we have like an ongoing call here. Okay, you're sort of streaming the call as you go. You're not really sure when it's going to end. Okay, so think about that case. So this is a voice. The data compressor takes the voice signal and compresses it down to a bit stream of minimum rate, minimum number of bits per second that you need in order to represent the voice. Okay? The data decompressor I'll say reproduces the source from this bit stream. Okay, so the data decompressor right here, okay, is designed so that if you just feed the bits that come out of the data compressor right into it, like suppose you eliminated the channel and just took this output and fed it right into this data decompressor. Okay, and these two boxes are designed so that this thing will satisfactorily reproduce the source from just the bit stream. Okay, so these two boxes are kind of designed like almost to circumvent the channel. So okay, so the data decompressor outputs bits, and the data decompressor is designed to take that same bit stream and then reproduce the data at the sink. Okay, the channel encoder, on the other hand, is designed to encode a maximum rate bit stream over the channel. Maybe I should say transmit instead of encode, otherwise it looks like I'm kind of using the word I'm defining in the definition. So transmit a maximum rate bit stream over the channel in a way that can be recovered. Okay. Okay, so the channel encoder is going to get a bit stream. This guy's going to map that bit stream to a signal that can go over the channel. So a light intensity signal that can go over the cable, or a voltage signal that goes over the twisted pair, whatever. Okay, it takes bits, it maps them to an analog signal that goes over the channel in a way that you can recover the bits from the output of the channel. Okay, and the channel decoder is going to recover the bits from the output of the channel. And this is why I'd like more chalkboard. I guess we'll delete this picture. Okay, so the channel decoder okay, this is designed to recover the bit stream from the channel output. Okay, so all together, you take the data source, take the voice signal. Okay, you compress it into a bit stream, minimum rate bit stream. So the fewest bits per second you can get away with. That still represents the source satisfactorily, to the satisfaction of your consumer that you're given, sitting over here. Okay, so you get a bit stream. Okay, the channel encoder is designed to take the bit stream and send it over the channel in a way that you can recover the bit stream. And once you've recovered the bit stream, then you use that you decompress it to reproduce the source. Okay, that is the separation architecture. In some sense, you separate the data compression from the channel encoding, whereas a priori they're just kind of together in one block. Okay. So I've seen this architecture likened to like the OSI network stack. You're familiar with this? Like you have like in networking, you have like the application layer and the transport layer and link layer and MAC layer and physical layer and so on. So each layer there, it's basically like a hierarchical design. So each layer kind of relies on certain services from the layers below in order to provide services to the layer above. Okay, and just sort of simplifies the design by taking this big, complicated design problem and dividing it into sub-problems, each of which is a kind of clearly specified goal. So this is sort of like that. You have like 2 layers. You have like the lower layer and the upper layer. So channel encoding, moving bits over a channel is at a lower layer than data compression, right? And the interface between the two is this bit stream. Okay, perhaps a better analogy is hardware-software, actually, in computing, because there you have 2 layers, right? So you have this complicated problem. I want to build a computer that does something. Okay, how do I do that, right? So over the years, computer engineers, have come up with this hardware-software separation. Okay, so you have the hardware, you have the software. The interface between them is the instruction set architecture, right? And dividing things up that way provides a great deal of convenience and simplification and so on, right? Because provides for interoperability, right? So if you have like 2 different computers that execute the same or provide the same instruction set architecture, then I, as a programmer, if I'm at the software level, I can write a program for that ISA and it'll work on either computer, right? It allows for human specialization, right? So you can work on the hardware, you can work on the software, and the hardware engineer only has to implement all the instructions. It doesn't have to care about how the instructions are used. Software engineer just knows that there are certain instructions to play with and doesn't have to worry about how they're implemented in the silicon, right? Similar here, okay? So this is like the software, this is like the hardware, okay? And this provides for a certain amount of interoperability. If you use this design and you change the channel, you just have to change this box and this box, right? The data compressor, the thing that takes the voice and maps it to bits, that can stay the same. Right? Likewise, if the channel stays fixed and you decide you want to send an image instead of a voice signal over it, okay, then these parts can stay fixed. The parts that send bits over the channel, those can stay the same. And we just change this. We use an image compressor instead of a voice compressor. So it allows for a certain interoperability. Okay? Whereas back with the design we had here, if you change the source, you got to change the whole. So if you change the source, you got to change the whole design. If you change the channel, you got to change the whole design. Okay, here this sort of contains the change. This allows for human specialization also, right? You can focus on moving bits over channels. I can focus on reducing sources to the minimum number of bits. And then we just take your design, my design, we connect them, and we're good. Okay? Our economy is actually organized around this principle to some extent, right? So you have people who work for like Adobe Flash, okay, who are trying to compress video more efficiently. You have people who work for Qualcomm who are trying to move bits over channels more efficiently, okay? And the Qualcomm people don't have to worry about how video is coded, they just move the bits. Likewise, the Adobe people don't have to care about how bits get moved over channels. They just have to think about how to take video and compress it down to the minimum number of bits. Okay? All right. So there's some parallels between Shannon's results or Shannon's architecture and like hardware software. There's one important difference though. In hardware software, the hardware software divide, there's no theorem that says that division doesn't incur some loss. Dividing things up between hardware and software is in some ways kind of an artificial division, and you see that nowadays in research and computing, maybe even in the computing classes. So there's this constant pressure to kind of like break the divide, to do like hardware-aware programming and software-aware hardware design and stuff. Okay, and the reason is that division between the two incurs a performance loss, and it's somewhat artificial. So if you want to get like maximum performance, you've got to kind of break that divide and just design it as one big thing. That's not true here. Okay, so Shannon showed any performance you can get with this, with a general architecture, you can get with this one. So you incur no penalty. No penalty for forcing this structure on the problem. Okay, so that was his theorem. So Shannon showed The separation architecture incurs no performance loss. Okay, in the sense that any performance you can get with an arbitrary design, you can get with this one. Okay, it's not something we can state and prove right now. You got to get into what does performance mean. Your ultimate measures, you're going to measure like distortion here, like how distorted is the reproduction here versus here. Okay, so ultimately what Shannon shows is like any distortion you can achieve with an arbitrary design, you can achieve with this design. Okay. So this result has had a big impact. It controls the way we think about designing communication systems. We organize our economy around it to some extent. It's almost too successful, I think, okay, in the sense that nowadays it's hard to even conceive how you would do it any other way, right? Like, I mean, of course, if I want to move information, if I want to move an image, I like compress the image into a file instead of bits, and I move the file, right? Like, how else would you do it? That's what Shannon says to do. He says you want to move an image from here, over to Syracuse or wherever. Okay, you take the image, you compress it into a relatively small number of bits, and then take that long bit string and design systems that move the bit string. And at the other end, recover the bit string and then use the bit string to represent the file. That seems almost like a stating the obvious, right? Like, what's the alternative? Is like, I mean, maybe the reason there's no separation, there's no loss in doing separation, is that everything is separation, right? That's one way of potentially proving this, is to prove there's nothing beyond this architecture. So of course this is optimal, right? That's one possibility. Okay. In fact, there are architectures that don't follow this. There are designs that don't follow this architecture. What would be an example? I've mentioned one already. Okay, let me ask a different question, actually. Let me leave the block diagram up. So to some extent, we're blinded by the times we live in. Okay, let's put ourselves in Shannon's shoes, 1948. Sorry, circa 1948. Okay, so what would be some examples of communication systems that were in use in 1948? Radio. FM and AM. Broadcast radio. Others.
CW. Or I guess that is FM. How about just telephone?
Yeah, telephony. So wired. Telephony. Telegrams. So there's both wired and wireless. Telegraph. Others?
Morse was still used then, right?
More, yeah.
It's still a wire.
That's telegraph. Yeah. That it? Television. Sometimes I do this exercise, people insist on putting postal service up. I don't know where you want to draw the line here. If you want it to be electronic things designed by electrical engineers, or just like any way that people communicate. Smoke signals. They're still used by the Vatican, right? When they have a pope, when they elect a pope, they indicate it by putting smoke up the. Okay. All right. So here's the example I mentioned earlier, like this one. Okay, so the way, circa 1948, okay, the way the telephone worked is, the operator would connect you, okay, and then you speak into a microphone. the microphone creates an electrical signal that goes right over the wires carry it to the other side, it then goes into a speaker, right to the person's ear, okay? That's the overall system, okay? Would you say that adheres to this architecture? No. The defining feature of this architecture is that the source gets reduced to bits, and the bits are reproduced exactly at the other side. Okay, so you have this bit stream that's common to both sides. Okay? That's the defining feature of this. That communication system, wired telephony circa 1948, was a purely analog system. Did not follow this architecture. This one did not. FM, AM radio. What do you think? No. There are no bits anywhere. There are no bits being moved. Okay? AM radio is the simpler of the two. That's almost like telephony. It's like you're talking to a microphone. Okay, you create an electrical signal. You just mix it with a sinusoid. They multiply it by a sinusoid that mixes it up to a carrier frequency. You put that on the antenna. Okay, and then at the receive side, you just mix it down, low pass filter it, listen. Okay, nowhere are you reducing the voice signal or the music, whatever you're trying to send, to a digital message that is recovered at the other side. Okay, nothing digital about it. So this does not follow his architecture. This does not follow his architecture. This did not follow his architecture. TV was also analog. It's amazing how they got analog TV to work, actually. This is something that we don't really teach anymore. I took classes in it when I was an undergraduate. And we had like this raster that kind of moved, okay? And then the electromagnetic wave, the amplitude of it would kind of vary depending on whether how bright the light should be as the raster was moving, okay? There's no bits. Okay, there's no MPEG compression of the video. Okay, it's all just like this purely analog thing, right? What about this one? Telegraph. Yeah, you could probably say it. I mean, they wouldn't necessarily write it down as bits. I mean, if they had a text message, I mean, telegraph was like sending text messages on some level, right? And they also had shortened ways of expressing words to kind of minimize the character count, just the way people using text messages do now. So there's an interesting parallel there. Okay, now the people in the telegraph office would not necessarily create a stream of bits, okay, and map the stream of bits to signals. But still, there was something digital, though, right? They'd map the text, I guess you could say like dots and dashes, maybe. They'd map it to Morse code, dots and dashes. The dots and dashes are sort of equivalent to bits on some level. And they map it through, and the dots and dashes would be recovered, presumably exactly, at the receiver side, right? So you have this digital information that's recovered exactly at the decoder, right? So that does fit the architecture. Okay, Postal Service maybe you could argue too, it's debatable, okay? All right, so if you're Claude Shannon, this is the world you live in. If you're Claude Shannon in 1948, this is the world you live in, right? I think it took a certain amount of clairvoyance, okay, to see that this architecture was the right way of thinking about communication systems. I can tell you, if I was a Bell Labs engineer, if Bell Labs would have hired me circa 1948, and I took a survey of the landscape of communication systems, you know what I would say? I would say analog communication is the future. Look at this trend. Who's making all the money here? Less so here, right? Less so here, right? These are the new technologies. These are the exciting technologies. This is where the action is. It's clear where the future's headed. And Claude Shannon, I think it took a tremendous amount of clairvoyance on his part to say, this is a technological dead end. And so is this, and so is this. Okay? And these seemingly 19th century technologies are actually the way we should be thinking about communication systems. Like this. And he was right. It's amazing, actually, that he could sort of transcend the technologies around him and recognize this fact. And he was right. And he was so right that now when we look at his proposed design, it's hard to imagine doing it any other way. Okay? Okay, so last bit before we go. Actually, I won't write anything. Let me just say one last bit before we go. Okay, so I said we organize our economy around this way of thinking. We organize our classes about this way of thinking too. Okay, so we have some classes that just focus on moving bits over channels. We have other classes that discuss how to take sources and map them into bits. Okay, Could you not do that? Just give me like 30 seconds, okay? Okay, there are some classes that talk about how to map sources into bits, and some courses that talk about how to map bits over the channels in a way that can be recovered. And the idea is you hook them together and you get a complete system, okay? This class is purely about this, how to move bits over channels like this. We're not going to talk at all about what the bits represent, how you might send an image and so on. Our mantra is just move the bits, okay? And there are other classes where you talk about how to take a source and map it into bits so that when someone else transmits them, okay, you can put those bits to good end. All right, we'll end there. I will see you Thursday.